A Hengeveld, I'm the Director of Marketing for the High Performance Computing business in the data center group at Intel. And I'm responsible for marketing activities in the supercomputing area and missing middle area and up and down the spectrum of HPC, and also for some strategic initiatives that go between the workstation business and the HPC business. So there's a couple. The first one is at the high end of the HPC market, there's a continuing drive for the delivery of cycles in support of research and development, research in new technology, new science, new learnings in general. It's continuing to drive up the application expectation for these dense, highly parallel systems that we build in HPC. The problem is, of course, that there is complexity boundaries that we're going to run into in terms of how you program these complicated systems. And the second element of this is that there's power boundaries and resiliency boundaries. That is to say, as you scale out the number of elements in a system, how long will the system stay up? How long will it stay operational? So on the one hand, there is building the ever larger system and managing and making it function well. And the second aspect of it is that the HPC market has a large collection of people. What's the right way to say this? There's a group of people in the middle market that are believed to be not participating in using HPC today that could be.
Okay.
And how we bring those people in to be served by the capabilities that we have in HPC to improve their performance as developers, designers, architects, and researchers is a key challenge as well. I did talk in the ISC middle market day yesterday, where I characterize these group as three groups of people that are involved in this. The first group of people are underutilizers of HPC who have the technical knowledge for HPC but lack the economic capability to access and build the larger HPC systems that they might need to map to their models that they're trying to develop and research. The second group is currently using workstation class technology, is doing things like Autodesk or SolidWorks or 3D Studio Max kind of stuff, but can't access the compute systems because they lack the skill set. They lack the embedded knowledge of how to use these more rich models, how to develop them, how to debug them, how to make them work effectively, and then how to effectively run them. And the third group of people is just people who don't use HPC at all, but I don't want to deal with it. I think expenses is a second issue to the complexity of using it. So HPC systems require a lot of knowledge to know how to use. I mean, how do you provision an HPC system? How do you gain access to the capabilities you need in that system? How do you program to the metal? How do you merge together all your models and run them in an effective way? There's lots of complex elements in the stack of a normal HPC system. How do you make sense out of all of that and bring all of that back to the application you're trying to develop, the science you're trying to do, or the model of the product you're trying to do? All of that's hard, and I think the social barriers and the skill barriers are actually larger barriers than the cost barriers going forward. Today, the startup cost for this kind of stuff is significant. Absolutely, that's a factor today. But in the future, I think it's going to be less of an issue. So many of these people are not actually programming stuff today; they're using applications. So if people are programming, yes, an easy step. Those are the people in the first category. They use HPC today, but they don't have the economic access to broaden that, to broaden their participation. It's the second tier people who are not programmers today. They don't view themselves as a programmer. They view themselves as architects. They view themselves as digital content creators. They view themselves as product designers. They view themselves as silicon chip heads. They view themselves as researchers in climate or energy or something. And they don't think of themselves fundamentally as programmers. And so, getting through that usage paradigm is an essential step. So in order to get to exascale from where we are today, if you take a look at the #1 system, it's 8 petaflops on the new list. So you got to go up about 120 times. So what we said today was 100 times. But to get to an exascale from today, you got to go up 100 times in performance. But if you went up 100 times in power, you'd have, you know, a pretty good-sized nuclear reactor running to run a data center.
Yeah.
And at those levels, you only have one of those in the world. And Intel's not interested in building out exascale as capability where there's only one in the world. It doesn't make sense. Exascale applications will consume many more than one system of this class. And power is probably the #1 barrier to making it cost effective to run this class of compute. And so you know, you need to have a relatively low cost energy delivery infrastructure and a relatively low cost to operate an exascale system for it to be a practical solution. So part of the reason we choose the 20 megawatt you know, environment to target is because it's such an essential element of the operating cost of the system as a whole. Oh, it's very significant. So the notion in a mic architecture is that you trade off parallelism, increased parallelism, lower clock frequency to achieve the same performance level. And when you do that, you actually lower significantly the power, because power is a function of frequency squared. When you lower frequency and increase cores, you can significantly reduce the operating power to produce the, you know, the flop level that you're trying to produce. You trade generality. You trade single-threaded performance when you do that. So if applications are well suited to this broad parallelism, very regular applications, data that's organized in kind of the right way, memory architectures that are organized in the right way, this trade-off makes sense. For a significant percentage of the applications in the industry, the Xeon class architecture is still the right architecture to use for HPC. Why? Because you're not doing just one workload. You're doing a wide range of workloads that have a combination of effects between I/O and memory and compute that a Xeon class solution will be the best for. But as you look forward, we want to be marrying the benefits of the mic architecture with the benefits of some of the more general-purpose platforms to create a system that has the power efficiency and leverages the parallelism that we're talking about for the class of applications that we think need it. So mic is fundamental, is an essential element of our overall strategy here. So the notion of bringing Moore's law to 3D means you've got an entire another dimension. So as you're scaling the resolution, which we continue to do, you know, at many generations yet, you're also scaling your ability to provide detail within that finer resolution. So you're putting more details in a physical planar space of the silicon. So what that does is it creates more features and more feature density. So Intel says, you know, we look ahead, we don't see an end to Moore's law. This essential technology has got you know, many more cycles of process before we reach its limits, and by the time we reach its limits, we'll figure out new ways to do it. Adding the third dimension is a vital step to this. So the rest of the system becomes significant challenges as we talk about what we're talking about with the exascale stuff and the exascale vision we have and commitment we have. Storage, memory, I/O are all part of the total equation to deliver performance. And all of those have to have technology breakthroughs. And when we say we can't do this alone, it's because we have to do this with partners in each of these other ecosystems. We have to have breakthroughs in storage technology. Clearly the spinning disk is not going to be the answer in 2018 to get to an exascale system. We have to get breakthroughs in interconnect technology. We have to get breakthroughs in how memory systems are architected to deliver information to the compute cycles that makes up an exascale machine. All of these things are going to require significant work, significant change in the way we think of the power.